Hello everyone, welcome to the fourth lecture of VLSI Interconnect course. Today's topic is Elmore delay in interconnects. In the previous lecture, we referred to the original paper by W.C. Elmore and we saw how Elmore delay is defined. We saw that if we define delay in a different way, which is like the centroid of the area under the curve of the derivative of output voltage. So, in that case, if I define it like this, then my delay comes out to be the dominant time constant. We saw with an example. The general steps involved in getting Elmore delay were we get the transfer function, we then expand it in the powers of S and then collect the coefficient of S. Now, in this lecture, we will be applying this Elmore delay to the RC ladder networks. We will take 2-stage, 3-stage RC networks and then we will generalize it to n stages of RC ladder networks. And then we will see that in the limit of the distributed RC interconnects, what expression do we get for the Elmore delay. So, let us get started. So, here is a quick recap of where we stopped. In the last lecture, towards the end, we solved the RC delay circuit. We solved the RC circuit like this. For that, we computed the transfer function, we expanded it in the powers of S, and we got the delay TD like this. Now, what is our aim? Our aim is to get the Elmore delay of an interconnect, and for our interconnect, we have a structure like this. We had solved this in the limit x going to 0. So, in that case we got a diffusion equation. Now, we want to get an Elmore delay, we need a system transfer function. So, we now taking the Laplace domain approach for solving this. So, here before we proceed, let us again recap few things about this interconnect. We had divided this interconnect in small segments. Here R and C was your interconnect resistance and capacitance per unit length. So, the units of R and C was in per unit length, and then delta x, when you multiply R with delta x, that gave you the resistance of this infinitesimal segment. Similarly, for the capacitances, if the length of your interconnect is L, then the total number of such elements would be n given by L divided by delta x, and in the limit when you are in the distributed limit. So, in the distributed RC connect limit, your delta x was going to 0. So, obviously, when your delta x goes to 0, then your n goes to infinity. So, you have infinite number of these very small small segments, which you then aggregate to get your interconnect. Before we can tackle a problem like this, let us start with simple cases of 2 stages and 3 stages, right. So, before we need to first get what would be the Elmore delay for n such RC stages of networks, and then we have to apply the limit n tending to infinity in that to get what will be my Elmore delay. But before that, let us first start simple. Let us take the case of 2 networks. For a single case, for a single case R1 C1, we solved it in the previous lecture. What happens if you have 2 such stages? So, here let us see what we can do. So, here it becomes easier if I define a impedance, input impedance like this. So, Z1, and I have also defined a voltage V1 here. So, my output, which is actually my output is V out of S divided by V I of S, where my V out of S is given by V. So, V 1 by S into, so this would be, so this is my V 1 here. So, my V 1 of S, and this is my this impedance is 1 by C S, this is R 2. So, relationship between this will be simply R 2 plus 1 by C 2 S into this will be C. So, this will be C 2 of C 2 of S. So, finally, your V out of S will be related to V I of S as per this equation. Now, we had defined my Z 1 here. So, my V 1 of S would be related to my V I of S like this, right, as per this equation. So, this is my Z 1, and then this Z 1 is the parallel combination of 1 by C 1 S and R 2 plus C 2 S. So, whatever was this impedance, so R 2 plus C 2 S. So, this will be parallel combination, right. So, when you substitute this, you will get Z 1 like this. So, I would strongly recommend that you pause the video and then do the remaining part of the solution on your own. So, what you have to do is you have to compute Z 1 like this, substitute this Z 1 here. You have got a relationship between V I and V 1 and Z in, and then you have got a relationship between V out and Z 1. So, you substitute that here to finally get your transfer function. Note that you would be getting terms in an expression like this. So, I would again strongly recommend that you do this derivation on your own to get H of S. Once you get H of S like this, you will have this expression where there will be 1 divided by 1 plus 1 term with a power of S, and then there will be other powers of S square, and so in this case we will get only till S square. So, then you bring it in the numerator, apply this binomial expansion, and you will be getting an expression like this. So, this in here is your Elmore delay. So, this is your Elmore delay. So, if I write this Elmore delay, I can write it like this. So, so I can collect it. So, there are 3 terms now in this. There are 2 ways of writing it. So, first let us see what is the coefficient, I mean what is the term of C 1. So, the term of C 1 is R 1 into C 1, R 1 into C 1. Then there is the next term. So, let us then collect terms of C 2, and for C 2 you have R 2, you have R 2 plus C 2, right. So, this is R 1 plus R 2 into C 2. So, if you look at this network, if I want to look at this delay, how can I analyze this? So, there is a first capacitance C 1, that C1 is multiplied by R1. So, there is a path like this. Then there is the second term which is C2, and then there is a path like this. So, a way of looking at it is you have a capacitor C1 that is charged by the resistor R1. That is one part of your delay, one component of your delay. The second component is you get when you have this C2, and then C2 is charged by R1 plus R2. So, for C2 you have R1 plus R2 here. This is one way of looking at this. So, you take the base as your capacitors, and then look at what were the resistors that were charging this capacitor, and then it looks like there is a superposition of, or say the addition of time, right. So, another way of looking at this same delay is that you collect the resistors as your base. So, you collect the resistor here R1. With R1 there is only one capacitor, so with R1 there is one capacitor C1 and C2. So, you write it like this, R1 into C1 plus C2, and then with R2 there is only one term of C2. So, with R2 you have C2. So, if you look at this, now your base is resistor. This resistor charges both these capacitors. So, when you want to reach from this point to this point, your resistor is charging C1 and C2. So, it is charging all the subsequent capacitors which are there. Then you go from this point to this point. In this point your resistance R2 is charging your C2. So, this is another way of looking at the same circuit. So, both the expressions are the same. However, I personally prefer this approach, and why, that will become clear in the next lecture when we generalize this for branched interconnects as well. Now, let us extend this analysis to the case of 3 stages. So, when we go to 3 stages, you have a circuit like this. Now, what you want to find the Elmore delay for this network. There are only 3 stages, but it seems that it can become complicated. So, let us break it down into simple steps. So, let this be the impedance seen from this point be Z1, impedance seen from this point be Z2, impedance seen from this point be Z3. Here this is V2, the voltage at this point is V1. So, then what we can do is we can what we want finally, we want V out by V in, right. This is what we want to find out. So, what we will do is we will go in stages. So, we will first find out what is V out of S by not V1, sorry, what is the voltage here, V2 of S. So, V2 of S. So, here this is a simple voltage divider. If this is Z3, this impedance is Z3, this is Z3 divided by R3 plus Z3, and here your Z3 is equal to 1 by C3 into S, right. Now, what about the second part? So, now you want the relationship between V2 and V1. So, your V2 of S divided by V1 of S is given by is given by the impedance here of this entire network. So, what is that? So, you have Z 2 divided by R 2 plus Z 2, where your Z 2 is a parallel combination of this 1 by C 2 S and this one, right. So, your Z 2 is a parallel combination of 1 by C 2 S with R 2 plus not R 2, R. So, this plus into R 3 plus Z 3 whole divided by 1 by C 2 S plus R 3 plus Z 3. Similarly, your V 1 of S would be related to V in of S as per the relation here. So, now Z in is the impedance seen here. So, your this is Z in R 1 plus and your Z 1 is parallel combination of 1 by C 1 S into R 2 plus Z 2 whole divided by 1 by C 1 S plus R 2 plus Z 2. Now, you have to multiply all of these while substituting this. So, again I would strongly recommend that you pause the video and do this, complete this derivation on your own. It looks more complicated than it actually is, because once you start substituting, I mean once you multiply say these two terms, you can see that this R 2 plus Z 2 would cancel out with this term here. Similarly, R 3 plus Z 3 will cancel out with this term here, R 3 plus Z 3 here. So, these terms will cancel out, and then finally, you will again get an expression like this. There would be other terms of S square and higher. We do not require that in our analysis. So, what we would be doing then is again bring this in the numerator with power of -1, expand it using binomial expansion, and you will get an expression like this. So, here in this is your Elmore delay. Again we can arrange these terms. One is that you look at this in this entire thing. But now, suppose you are given an RC network, like how do you get this expression? We do not expect you to memorize it, right, for each type of circuit. So, if I look at, again let us collect terms. So, there are two ways of doing it. Let us collect the term of capacitor. So, with C 1 I can see there is no C 1 here, no C 1 here, no C 1, no C 1. So, with C 1 there is only R 1 and C 1. Then with C 2, let us see how many terms are there. So, with C 2 there is R 1 and C 2, there is this term, and then there is this term of R 2 and C 2. However, there is no term of C 2 with R 3. So, the second term is R 1 plus R 2 C 2. Then, if I look at the third term with capacitance C 3, so there is R 1 C 3, R 2 C 3 and also R 3 C 3. So, now I have R 1 plus R 2 plus R 3 into C3. Again, let us again practice the way if I had a circuit like this and I wanted to get an Elmore delay, how would I get that? So, I take the first capacitor, I look at the resistor which is connected to this, so which is contributing to this charging. So, there is R1 and C1. So, there is this first path here from this point to this point. Then you go to the second capacitor has this thing. So, from here to here if you want to reach, you have to get this R1 plus R2 charging C2. Then you go to the third capacitor is being charged by this. So, it is you can see like you can look at it like this, that time required from this point to this point is R1 into C1 from this point to this point. So, basically then you are charging C2. To charge C2, both R1 and R2 are contributing. So, there are terms of R1 and R2. Then you have to charge this C3 from this point to this point, and all three resistors are now contributing to this charging. So, there are terms of R1 plus R2 plus R3 and this one. Another way of arranging the same thing can be that we take the base as your resistors, right, and then you write it. So, if we write it like this, what you would be getting is that you would be having a terms of, so let me write it from here. So, with R1 there are all three capacitors, right. So, R1 into C1, R1 into C2, R1 into C3. So, if I then collect terms with resistors, I have C1 plus C2 plus C3. Then, if I take the second resistor, similarly I will have term of R2 into C2 plus C3. So, R2 into C2 plus C3, and then R3 into C3. So, now again if I want to look at the interpretation of this, what is happening in terms of resistors is the following. So, I have these resistors, this point to this point if I take my resistor as the base, this resistor is charging all the three capacitances. Then I go from this point to this point. In this case, I am getting only this and this. So, I am having these two, and when I go from this point to this point, then I have only this capacitor. So, this capacitor comes there, right. So, this is for the three stages. Now, let us recall what was our aim. So, our aim was that we get the delay for this type of interconnect, Elmore delay for this type of interconnect. Now, it seems that we are closer to this. So, with our analysis of say 2 stages and 3 stages, we can then generalize this to n stages of RC networks. Again, there are two ways of writing this. I will write it in both ways just to practice with different ways of looking at your interconnect. That will help us in analyzing branched interconnects more specifically. So, if I have something like this, what I can do in the first approach, what I was doing is that I was collecting the capacitances. So, this capacitance is being charged by R1. So, I have R1 into C1. In the second term, what I had was R2 into, so my second capacitor was charging R1 as, so not charging, it was charged by R1, charged through R1 and R2. And similarly, if I had C3, then I would have had something like summation I going from 1 to 3 R I, and then so on. I can write for the kth capacitor, that all the previous resistors should be incorporated. So, should be going till k, and then this would be R, this would be R I, and then the final term would be going to N R I into C N. So, I have write this. So, I can write this as a summation of summations of this form. This is one way of writing it. There can be another way. In the second approach, I take the base as my resistors. So, in that case, what I do is my first resistor is R 1. R 1 is then charging my all the subsequent capacitors. So, my capacitors are now, I can start by writing the summation 1 going to N C of I. Then, if I take the second resistor, so in second resistor I will be having this summation. Now, in the second resistor my first capacitance is not there. So, I only require the succeeding capacitances on my path. So, I will be having a summation I going from 2 to N C I plus this can go on. So, for R k I can write summation going from I is equal to k to N C I, and then this goes on. So, the finally my final term would be R N into C N. So, my final resistor will be charging only the this capacitor C N. Right. So, I can write this long expression as a summation over summation. So, I can finally get an expression of this form. Both these expressions are identical, it is just a different way of looking at it. When we look at the branch interconnects, you will appreciate why different approaches can have different utility for different type of networks. Right. So, now let us come to the main problem of Elmore delay in an interconnect. So, in the interconnect what we have is this. So, I have an interconnect like this, I have segmented it into delta x. Each of this element has, so I am showing the top view. So, each of this has some resistance and capacitance per unit length, and if I write it like this, I get an something like this form. So, for this if I now want to write, I have not applied the limit, there are n elements here. So, right now my n is equal to L divided by delta x, or my I can write my n into delta x is equal to L. So, if I have this, then I want to write my delay. So, let us take the first approach. So, I take the first capacitor. So, my first capacitor is, so I have R into delta x, that is charging C into delta x. So, this is this part. Then I have the second one. So, this is 2 into R. So, this is an uniform interconnect. So, all these segments are identical. So, you will have 2 into R into delta x into C into delta x, and so the third term would be 3 into R into delta x into c into delta x plus this going up till infinity, sorry, not infinity yet. So, this finally going into n terms. So, so there will be n into this. So, n into r into delta x into c into delta x. I can then rearrange this to write it like this. So, I can take r, I can take my r and c outside, there would be a term of delta x square, and here would be 1 plus 2 plus 3 plus going all the way up till n. So, what is this? What is this summation? So, this summation is I can write this as n into n plus 1 by 2. So, my T d now becomes a simple expression as R c into delta x square into n plus 1 by 2. Now, I can rearrange this, I can take this n out, and once I take this n out, what I get is R into c into delta n, sorry, n into delta x whole square divided by 2. Note that we had this expression here. So, once we have this, my T d simply becomes my so my T d simply becomes R c into L square by 2 into 1 plus 1 by n, right. So, this is my expression. Now, I am well placed to go to the distributed model. So, now I apply the limit delta x tends to 0 or n tends to infinity, and if I apply my limit here, limit n tending to infinity in this, what I get is my delay, my Elmore delay as R c L square by 2. So, this is for a uniform interconnect. So, for a uniform interconnect with resistance per unit length and capacitance per unit length given by R and C respectively, the Elmore delay is given by R c L square by 2. You can see here this Elmore delay scales with the square of length. For the lumped model which we had seen, your n will be equal to 1, right. So, there is only one segment in that case. So, if I substitute n is equal to 1 here, my delay would be coming to be this case. And if you recall the first lecture, in lecture number 1, we had seen that your that was not Elmore delay, that was the R c delay, that was coming out to be R c L square by 2. So, here the actual delay, the Elmore delay is less than that for the lumped model by a factor of 2. So, the lumped model was actually overestimating the delay by a factor of 2, and this also makes sense because earlier what we had said was you had a resistor and then that resistor is charging the entire capacitance of your interconnect. However, that is not the case. Your resistance is distributed and your capacitance is also distributed throughout. So, I mean if you look at the way this would be charging from our this distributed model, it makes sense that your lumped model was overestimating your delay by a factor of 2. So, in the let me summarize what we have seen today. So, in today's lecture we saw the Elmore delay for RC ladder networks. We generalized it to n stages, and from that we applied the limit n tending to infinity to get the Elmore delay for distributed RC interconnect. Here we saw that the lumped model was overestimating the delay by a factor of 2. So, in the next lecture we will be continuing with this discussion. We will be taking specific cases of RC networks. So, we do not have a single path now, we will be having branching in your RC network. So, we will form a tree of RC components, and then we will see that how that extends to analyzing our branch interconnects. That is all for today. We will meet in the next lecture. Good day.